Good afternoon, ladies and gentlemen. Welcome to this IAS distinguished lecture, co-hosted by IAS and also Energy Institute. Today we are so fortunate to have an outstanding speaker, Professor Huiming Cheng from Institute of Metal Research in Shenyang. A Chinese academic of science. So before, let me give a brief introduction to Professor Cheng's background. Professor Cheng received his PhD in material science from the Institute of Metal Research, Chinese Academy of Sciences in 1992. He then joined Nagasaki University, Japan, as a research associate for engineering. He returned to the Institute of Metal Research in 2001, and then has been the director and also the professor of Advanced Carbon Division of Shenyang National Laboratory for Material Sciences. Professor Cheng is a world-class scientist in material science, particularly focused on carbons. Okay. Professor Cheng got a very interesting WeChat nickname that is Mai Tai Wong. Shao Tai Wong, okay. Shao Tai Wong, yeah. That is his WeChat nickname. Yeah. So Professor Cheng has been working on synthesis and also application of carbon nanotubes, graphene, and other low-dimensional materials. In particular, over the past decade, Professor Cheng has been working on developing different carbons for energy storage application. So Professor Cheng received a large number of honors and award. For example, he was elected as academician of Asia Pacific Academy of Material and also Chinese Academic of Sciences. He's also elected fellow of World Academy of Sciences, and the award he has been received, including the second-class Chinese National Natural Science Award, and also the Charles Patinos Award by the American Carbon Society, and also the Award for Scientific and Technology Progress, that is a second-class award, by Chinese Ministry of Industry and Information Technology. So today, Professor Cheng is going to talk about nanocarbon materials for electrochemical energy storage. So without further ado, please join me in welcoming Professor Cheng.
Good afternoon, ladies and gentlemen. It's my great honor to be here to give this lecture. I have been visited this university for a few times, but mostly for attending scientific conferences. So this is my first time to come here to give this talk. I would like to thank Professor Zhao for his invitation. So now I'm working actually for two laboratories. The first one, as Professor Zhao introduced, I have been here for many years after I came back from Japan in 1993. And then in 2001, I started this new laboratory, Advanced Carbon Research Division at the Shenyang National Laboratory for Material Science. Very recently, I was invited to join the Tsinghua Berkeley Shenzhen Institute to establish this new laboratory, low-dimensional material and device laboratory. The Tsinghua Berkeley Shenzhen Institute is a brand new institute co-established by Tsinghua University and UC Berkeley. In 2015, September, so it's very new, only about 1 year. I joined this institute since last June. So now our laboratory is less than 1 year. So we will have a birthday, 1 year birthday soon after months. So today I'm going to talk about energy storage. So in fact, we're working in this field on nanomaterials, in particular carbon nanotubes and graphene materials, from synthesis to application. So we are also working on materials and devices for clean energy application and on high performance graphitic materials because as Professor Zhao introduced, I'm mainly working on carbon, so I'm a carbon guy. So we have to work on also bulk carbon material in addition to those nanocarbon materials. Today, I'm only going to talk about some of work of nanocarbon materials in energy storage. So in addition to those more fundamental oriented research, actually, we also develop some practical energy storage materials for commercialization. So we have two companies. One is producing anode material, another one is producing cathode material. So as we know, the energy consumption in the world is increasing and day by day, year by year, because the world population is increasing every day. And also, the living standard of human beings is increasing, in particular for developing countries like China and India. That makes the energy consumption is increased greatly, as I show you from this figure. However, if we only depend on the fossil fuel, it will cause a great deal of problems, including air pollution and global warming. As the Chinese is facing, as we know, we have smog, heavy smog in year long. And another problem is because the fossil fuel is limited, so that with the increase of the consumption, the fossil fuel will be used up someday. Some people said maybe several tens years. Some people said for oil, but some people said maybe longer, because we also discover some new oil field and coal field and so on. Anyway, I think maybe in some day those fossil fuel will be used up. So we have to develop some new energy, as Professor Zhao is doing. So we need to have those energy from solar cell, from solar energy and also from wind. However, this kind of renewable energy is dependent upon the weather and the climate. So we need to find some way to store the energy we obtained from renewable energy source like solar energy and wind energy. So one way is large-scale electricity storage. So Professor Zhao has been doing many work in this field, like flow batteries. And another big field is electricity storage for mobile application, including electric vehicles and also portable electronics we are using every day. So today I'm mainly talking about this part because I'm working on nanocarbon materials, and nanocarbon materials has many potential applications in this field. So now, let us look at the energy storage devices. So basically, right now, we can have two parts of devices for portable energy storage. One is battery. In recent years, mostly lithium-ion battery. Another one is capacitor, in particular supercapacitors. So for both devices, we hope to go like this way to increase its energy density and increase its power density. Here, I want to explain you the energy density and power density. For example, if we want to use battery in electrical vehicles, higher energy density means longer driving distance. Higher power density means faster speed, acceleration speed. So we need to go like this way. Even for portable electronics, we also need higher energy density. As you know, Apple phone probably cannot be used for 1 day. So if I can have a higher energy density, maybe you can use 2 days or 3 days. So we need. However, from this figure, this diagram plot, we can know that for battery and also supercapacitor, if we want to increase the energy density, the power density will be decreased. So this is a kind of a trade-off between energy density and power density. So therefore, we need to develop different kinds of material or optimize the materials for supercapacitors and for batteries. Even for the large scale storage devices like a flow battery, this is also quite important. So for recent years, in particular for recent 10 years after DOE paid attention to batteries, many scientists have developed quite many strategies of high performance energy storage materials. So this approach includes nanostructuring, nano-micro combination, core shell structuring, hybridization. For supercapacitor, of course, power structure control surface modification is very important. It's more important than battery. Of course, but for battery, it's also important. And also, the new device design and configuration design is very important. Even we have the same material, if we change the configurations, we may get a higher performance of the energy storage devices. To improve this property, as I mentioned, the most important one, energy density, power density, and of course, reliability and cost and lifetime are also very important. Carbon is a very special element and also very good material for energy storage. As I can see, carbon has a very good chemical stability and also good mechanical property if we make carbon into nanotube form or graphene form. And also we can control the texture and the microstructure in many ways. That's why we have many types of carbon. Carbon fiber, nanotube, nanofiber, activity carbon, and graphene, bulk carbon material, three-dimensional porous carbon material, and so on. Mesoporous carbon, as I show you here. So many morphologies. So which means our scientists can do many things on carbon. And also the resource is quite rich, so the cost is not high, which makes carbon material is a very good material for many applications. In particular, since 1990s, scientists has found carbon can have those kind of nano form, such as carbon nanotubes, graphene, even graphite, and also mesoporous carbon. And then this carbon powder is quite important as well, because in 1991, Sony has invented this lithium-ion battery using carbon powder that makes the portable electronics become available for every people. So today, I'm only going to talk about how to use carbon nanotubes and graphene in energy storage. So we know carbon nanotubes and graphene materials have many unique properties and structure from one dimension to two dimension, and also nano confinement effect, very good thermal and electrical conductivity, good mechanical properties. So this area, and quite important for energy storage, because this nanotube or graphene are quite easily to be functionalized. So we can do many things. And also carbon is quite stable, except oxidation at high temperature in oxygen or air atmosphere. So therefore, we can use those materials as electrode material to improve this performance, and then to get a battery cell with a very good performance. Therefore, carbon nanotubes have become core components in energy storage devices as many functions, such as active substance, conducting network, catalysis or support, and also interface controller, or as simply a substrate for making composites or hybrid. And also can be used in many types of energy storage devices, including lithium-ion battery, sodium battery, and other iron batteries like zinc iron battery and so on, lithium sulfur battery, lithium iron battery, or supercapacitor, or flexible battery, and so on. So from now on, I will talk some uses or applications of carbon nanotubes and graphene in energy storage separately, mostly based on our research work. So we know that Professor Ijima at NEC first report the carbon nanotube structure in 1991. So after then, with the development of many groups in the world, right now we can produce carbon nanotubes in a large quantity. So in mainland China, we have three major producers. One is Shenzhen Nano Harbor, very close here. Another one is called C Nano. And the third one is in Chengdu. So the total production amount is probably around 1,000 tons per year. So the Nano Harbor is about 300 tons capacity. C Nano may be more than 500 tons capacity. And we had a statistic data. So last year, probably we used about 500 to 600 tons of carbon nanotubes in lithium-ion battery. Because carbon nanotubes has those properties, in particular, very large aspect ratio, and also a hollow interior space. So therefore, we can make a good conductive network from carbon nanotubes. We can also use the spatial confinement of high-capacity active material into the hollow tube. So why we can use carbon nanotubes to form three-dimensional network and have very good performance? So this is a very simple drawing to show that. Basically, we can well disperse carbon nanotubes among the electrode materials and to form a very good connection between them. And during charge and discharge, because the resonance of the carbon nanotube network, so the electrode materials are very difficult to detach from each other from the carbon nanotubes. However, if we use traditional conductive carbon block like this, so during charge and discharge, so the active electro materials will be detached from each other to have a very poor cyclic performance. So by using carbon nanotubes, we can enhance the transport. So as I show you here, so this is a very early work. So we are one of the pioneer group to first introduce carbon nanotubes into lithium-ion batteries. So as I show you, so with carbon nanotubes, so the cyclability has been greatly improved for many types of electrode materials. So here is lithium iron phosphide, and this one I think is graphite anode material. This cathode material. So we can make this carbon nanotube slurry, and then to make a network which is very well conducting. And then you can see here, in particular, at a very high rate capability, the capacity is still very high compared to carbon black conducting additive. So as you may know, the C is a unit for charging and discharging. 1 C usually means 1 hour charge and 1 hour discharge. So the 10 C means 6 minutes charge and discharge. That means power density. So you can charge it very fast, you can discharge energy very fast, then you get a very high speed for your electric vehicle. So then after years effort with quite a few groups from my institute, from Tsinghua University, so now we can largely use carbon nanotubes in lithium-ion battery to improve the performance of high-performance battery like we used in notebook and in electrical vehicles. So the main producer I already said, C-Nano, Shenzhen Nanoport, and Shenzhen, it's called the Shenzhen Nanoport, not Lala Harbor, I'm sorry, Shenzhen Sanshui, and so on. So here we use multi-wall carbon nanotubes. Multi-wall carbon nanotubes has a very low cost compared to single-wall nanotubes. But we still want to use single-wall nanotubes because single-wall nanotubes has very small diameter. If we use it, probably we can use a very small amount of single-wall nanotubes to replace larger amount of multi-wall carbon nanotubes. And as we know, battery, in our battery, we have active cathode material, active anode material, we have a current collector, we have a separator, electrolyte, we also have, as I just mentioned, additive and binder. So only active material are contributing energy. Other materials are supporting material which didn't contribute to the capacity at all. So if we reduce those inactive material. That means we can improve the battery performance even we use the same active material like carbon. So therefore, we also we work with Shenzhen Nanopod. We try to use single carbon nanotubes into battery. So as I show you here, so this data provided by a battery company, which don't want to want me to say which is. I'm sorry about that. You can see we can just add a very small amount, 0.06%. But we can get almost a similar performance with the capacity, with the resistance. And more importantly, you can see here, the discharge at a different temperature, storage at 60 degrees C for 7 days, the performance. You can, this single wall nanotubes, the same expansion, you can say, with aid of single wall nanotubes, the thermal expansion is very small compared to other additives. That means safety is better at high temperature. As we know, the Samsung had a big problem because of the safety of a battery. So if we have a very safe battery, of course, it's very important for portable electronics and electric vehicles. So now we are making efforts to use single nanotubes in batteries. So that's almost no scientific, but just application. But it's very difficult to do application. More difficult, I think, to then publishing papers in science. We have been working on that for more than 10 years, actually. As I show you, the first patent is around 2003. So then we set up a company in 2004. So it's very difficult to do that. Another aspect is to use the confinement effect of carbon nanotubes. So then we also can improve the performance of active materials. So we know that, for example, silicon has very high capacity compared to carbon. Carbon, the theoretical capacity is 372 milliampere hour per gram. But silicon has a theoretical capacity of 4,200. It's more than 10 times higher. But the problem is silicon has a very high volume change, expansion during charge and discharge. That means the electrode material will be the electrode will be very easily damaged during charge and discharge. Then just for a few cycles, the battery will fail. So therefore, we needed to control the volume change of silicon particles. So then we tried to fill the silicon nanoparticles into carbon nanotubes, I show you here. So we use this AO as a template, and then we fabricate carbon nanotubes and fill silicon into it in nanoparticle form, and then we remove the AO, we get this 100% silicon-filled carbon nanotube hybrid materials. So then we try to understand the mechanism. So this silicon nanoparticle filled into the carbon nanotubes, and then we study the electrochemical performance. As I show here, this is pure silicon. This is the carbon nanotube confined silicon, as I show you here, which has a much better cyclability than the pure one, and also much better rate capability. You can see here. So this is the current density compared to this pure one. Then we try to understand the mechanism. So we have done some in situ TEM. So this is a very simple TEM compared to Professor Wang's work. So we have this electrode with some lithium on it, and then we put this silicon filled carbon nanotube on another electrode. Then we can observe performance during charge and discharge, as I show you here. So you can see here. So after charging, actually the space has been filled because the silicon nanoparticle expanded, and even the diameter has been enlarged in some way, and also have changed the structure of the carbon wall. And also we have tried to investigate the flexibility of those material. We can say we can push it, and then after unloading, the carbon nanotube can return to its original morphology. That means this material has some flexibility, which may be important for making, may be useful for making flexible batteries. And this is another example. We can say that there's iron oxide particle, which also has quite a high capacity, confined into the carbon nanotubes. You can say we can investigate the structure change during charging. So, for example, after lithiation, we found that we can form this kind of structure, lithium oxide with iron nanocluster into the nanotubes. So this is a quite good way to investigate the mechanism or formation, deformation of electrical materials in situ in carbon nanotubes. But it is very difficult to do this kind of experiments. So easy to do. Okay, so I will move to the second part. We also can use graphene materials into energy storage. Even more interesting because graphene can have different kinds of morphology. So the single shade or graphene oxide with many functional groups. And then we can make a two-dimensional membrane, also three-dimensional structure. Porous structure. So with those kind of morphologies, we can try many applications. Again, graphene has quite many advantages. In addition to carbon nanotubes, graphene is more easily to be functionalized, and also quite easy to fabricate membranes, coatings, and three-dimensional structures compared to carbon nanotubes. If we want to use graphene in energy storage, the one basic requisite is we have to have a large quantity. Otherwise, it's very difficult to do application. So basically, we use graphene from chemical exfoliation method. Chemical exfoliation methods can be classified into these four types. So liquid exfoliation, solid exfoliation, oxidation exfoliation reduction, and interconnection exfoliation. So for those two methods, for all the methods, basically we use natural graphite. But for those two, we add some surface agent to add the exfoliation during the the silication or ball milling. But for those two methods, normally we needed to add some chemicals like those highly oxidizing agent or some salt. So for oxidation, exfoliation, reduction method, because after oxidation, the material we obtained is graphene oxide. It's insulating. So we need to reduce it into reduced graphene oxide to be used in energy storage. So here I show you some large scale produced graphene powder and suspension in cooperation with our company in Sichuan province. It's called Deyang Carbonyl Technology. And this method is by integration exfoliation. So with those material, we can very easily to make this membrane, and also quite easily to make a three-dimensional material as well. So therefore, we can use it for some practical application and also for some research. The first example is a practical application. So we can simply use graphene as a current collector coating. So as I just mentioned, battery, we have to use current collector in battery. Normally use copper foil or aluminum foil. So then if we coat a very thin layer on the current collector, you can say without graphene coating and with graphene coating, the performance has been greatly improved. This lithium iron phosphide, very popular cathode material. This lithium and lithium titanium oxide, anode material. So you can say for both materials, the performance has been improved. This is very simple one. So we don't publish any papers. We have a patent. So one company is trying to use it in industry. So another approach is like carbon nanotubes as conducting additive. So as I show you, so we can add this graphene material into lithium titanium oxide and to reduce the polarization and improve the capacity and also cyclability. As here I show you this 20 cell, which means 3 minutes charge and discharge, we still can have very high capacity. So therefore, maybe you heard many news from mainland China. So some battery company or some companies are using graphene into batteries. Yeah, we can improve the performance of battery, but not as so significant like some company claimed. Charging 10 minutes, the electrical vehicle can drive 1,000 kilometers. That's nonsense. Some people also ask me, can we use graphene material as anode material? So also we have tried this research many years ago, but we found that although the capacity is very high, but you can say the drop also is big, that means the irreversible capacity is very high as well. That means also very low Coulombic efficiency. So although we can have high capacity, but it's not practical. So I will say we cannot use graphene material, pure graphene material as anode material. But it is a very good matrix to making a hybrid or a composite with other high capacity materials such as oxide. We know oxide has very high capacity, but oxide are also very easy to agglomerate and has very poor conductivity. Oxide many oxides are insulating, and also big volume change during charge and discharge. So when we have graphene, so we proposed to incorporate those two materials together to suppress the agglomeration and volume change of oxide, and also to suppress the restocking of graphene. So, and also we found that because there are many functional groups and defects on those graphene oxide or reduced graphene oxide, so the oxide is ready to nucleate at those sites to form a uniformly dispersed nanoparticles of oxide. And also, graphene can form a highly conductive and flexible network. So in this way, we can improve the performance. And also, we can have different kinds of structures. So this is one of the earlier review for those kind of graphene hybrid materials. So include the anchoring, the sandwich, or layered structure, or roping structure, and so on. And also the process is quite easy, quite simple. So we have graphene or graphene oxide, we put into some solution, and then we put the oxide precursor into it, as I mentioned. So the oxide is ready to nucleate at those active sites to form this composite or hybrid materials. So here I gave you two examples. One is cobalt oxide. Probably this is one of the first paper for those kind of graphene hybrid. So as I can show you, those hybrid material has very good cyclability compared to the pure oxide, and also much better rate performance compared to the pure oxide. So you can say the oxide are nanoparticles on the graphene. And also, we have done those ruthenium oxide for supercapacitors. And similarly, we can get a very good cyclability compared to the pure ruthenium oxide. And based on the role of mixture, we found that we have a plus capacitance here. So which means between the oxide and the reduced graphene oxide, we have some synergistic effect to improve the performance. So what the mechanism for those materials? So we have investigated it from the microscopic mechanism, microscopic way and also microscopic way. As I mentioned before, actually, with graphene, we can form well-dispersed oxide nanoparticles, and also we can suppress the polarization of oxide particles, form conducting network, and prevent the restocking of reduced graphene. And from the microscopic way, again, we use this in situ investigation. So we have this graphene hybrid particles on this electrode, and then we have lithium in this electrode. Because lithium is ready to be oxidized to form this lithium oxide, so this lithium oxide can be used as electrolyte in situ the TEM. So then we can measure the diffusion of lithium from this part to this end. So then we calculate the lithium diffusion rate. You can say we have three model material. This one is nickel oxide on graphene with very strong interaction. This one is nickel oxide and graphene by mechanical mixture with a weaker interaction, and then nickel oxide nanosheets. You can see, compared to these two materials, this strongly interacted hybrid material has very high lithium diffusion rate, which means very high lithium reaction kinetics. So This is a movie you can show. I can show you here the graphene can prevent the volume expansion of nickel oxide. So this is a piece of graphene. This is a piece of nickel oxide nanosheets. You can see with the interaction between the oxide and the graphene, the volume change has been restricted very clearly. In this place, free nickel oxide place, you can say the volume change increase, and the volume is increased here. So therefore, we know that graphene's role in those lithium-ion battery or supercapacitor is to increase the lithium diffusion rate, improve the reaction kinetics, and control the interfacial expansion. Therefore, we can improve the performance of lithium-ion batteries. Okay. However, with more than 20 years, about 20 years development, the capacity or energy density of lithium has not improved so much, only about 1 time compared to the more ratio of more low in semiconductor industry. This speed is very slow actually. So therefore, we need to find some new batteries. So here, I will show you, we also can use use graphene in lithium sulfur battery. Lithium sulfur battery has very high capacity, and also the cost is not much. But the problem is very fast capacity fading or poor cyclability due to the insulation and nature of sulfur, and also short effect of polysulfides between the cathode and anode, and also, again, volume change during charge and discharge. So then we try to use graphene lithium sulfur battery by different approach, including confinement and chemical bonding, or simply to changing its configuration of the electrode. So I will show you some example. So first, we think because graphene is a layered material, so we may anchor the sulfur on the network of the graphene or rope it by the graphene. So we do find sulfur nanocrystals can be roped in graphene, and we can improve its performance, as I show you here. But this is our first approach, but we found that it's quite difficult because the process is complicated and the material we can obtain is very limited. So another way is we also thinking about chemical bonding to suppress this shuttling. Because we know that, I missed one slide anyway. So actually, polysulfide is a polar molecule, and the electrode also is a polar molecule. That means the interaction between polysulfide and electrode is a polar interaction. But carbon is non-polar molecule, like a graphene. So that means graphene and polysulfide has non-polar and polar interactions, which is weaker than polar interaction. So therefore, we think we need to introduce polarization on carbon by doping, or to use polar sulfates of metal oxide or nitride to improve the chemical interaction. However, with some DFT calculation, I will go through very quickly about this part. between the lithium polysulfide and the nitrogen doped graphene, or oxygen doped graphene anyway. So for nitrogen doped graphene, we can have different types of configurations, typically 4 types of configurations. So we can calculate the interaction between those configurations and the polysulfide, and also we calculate those polysulfide, the interactions between the polysulfide and those electrolyte molecules. So here we found that actually the interaction or the binding energy between the polysulfide and the electrode is about 1 electrovolt. Therefore, if we want to trap the lithium polysulfide on carbon material, we need to have this binding energy larger or comparable between the lithium polysulfide and the electrolyte. However, after calculation, we found that only clustered pyridinic nitrodoping, this part, has higher binding energy between the lithium polysulfide and the doped material. However, this clustered pyridinic nitrogen doped carbon material is very difficult to obtain. We have tried many experiments, but it's not so successful. So therefore, very recently, we are thinking to use this polar surface of nitride. So this vanadium nitride with graphene material. So then we can incorporate this material on a 3-dimensional graphene structure. And then we found that this lithium polysulfide has very strong interaction with those metal nitride, much higher than lithium polysulfide and graphene material. So that's only 0.74. So for this experiment, you can say this lithium polysulfide solution, yellow color, and it is difficult to be trapped by the reduced graphene oxide with many oxygen functional group. But it's easily to be trapped by the metal nitride, you can say graphene 3-dimensional structure. So that means we can use this kind of structure to trap lithium polysulfide. So here I show you the performance. You can say the performance is very high. It's close to more than 1,200 capacity, and also the read capacity is good. So that means this kind of approach is useful for lithium sulfur battery. But again, if we want to use this kind of material in practical lithium iron sulfur battery, it's not so easy. So we always think some easy way. Here I show you some easy way. We just want to integrate graphene and sulfur together into some kind of configurations. So the first configuration is we try to use graphene as current collector and buffer layer. So for lithium sulfur battery, we also need to use current collector, as I show you here. So here we changing the metal current collector into graphene. And also we have a buffer layer on the separator to improve the adhesion between the graphene and the active sulfur material, and also lower internal impedance and polarization. But most importantly, to adsorb trap polysulfide, which can be reused during cycling. So that's very important. So here I show you the results. This is the membrane, graphene membrane, current collector. This is a buffer layer coating. We have this 4 configuration. So this for both layer, by graphene. There's one layer graphene, another layer graphene. There's without graphene. You can see this two-layer graphene configuration has much, much better performance. So that's very simple. Maybe can be used practically. And we also try to analyze the sulfur distribution by the three-dimensional X-ray tomography. You can see here, about 70% of sulfur is trapped into graphene layer, and only 29% are passed through the separator. We have one step further. So we incorporate the two layer into one layer. This is our integrated structure, one layer structure. We have this active material, we have this graphene layer, and we have the separator. So graphene layer can be used as current collector and buff layer. So actually the functions are very similar to what I just showed you. So I will skip. So you can say we have the three-layer structure, sulfur electrode, graphene, separator. And again, we have a very good electrochemical performance, very nice cyclability even for 500 cycles. This is a very long, very big cycle in lithium, for lithium sulfur battery. And then very recently, we designed this structure. We call the sandwich structure. Because we use three types of graphene, highly conductive graphene. This layer is current collector. Highly porous graphene to host the sulfur active material, and partially oxygenated graphene in this layer to trap lithium polysulfide. So then we also can have very good performance, as I show you here, and a very low polarization. And then one more problem is basically for lithium sulfur battery, we only have very low sulfur loading, less than 2 milligrams per centimeter, square centimeter, and also very low sulfur content, less than 70 weight%. That means very low area capacity and very low energy density. So some years ago, we can make this freestanding graphene form with a three-dimensional intercollected power structure, very light, high porosity. So then we try to make a nested hierarchical structure by incorporate the sulfur on reduced graphene oxide, then put those hybrid material into this graphene form. So in this way, we can have a very high loading and also very high sulfur content. So then we can have a very good performance compared to the previously reported results. Our results is very much outstanding. Okay, I need to hurry up. So finally, we can also use those nanocarbons for flexible and smart energy storage. So as you know, the wearable electronics will become more and more important. And so, of course, we also need our battery to be light, thin, and flexible. So I always use this term, Chinese term you may know, 白富美. So we needed to have flexible batteries, which can be incorporated into portable electronics. So actually, this kind of flexible device can be classified into bendable devices, stretchable devices, and compressible devices. We can use different kind of carbon materials, such as graphene membrane, carbon nanotube fibers, and also these three-dimensional structures to make this kind of different types of flexible energy storage devices. In addition to carbon nanotubes and graphene, actually we also can use carbon cloth, carbon fibers, and conductive papers, and so on to make different types of prototype energy storage or flexible lithium-ion batteries. So we also have done some work. So again, we use this graphene foam-based flexible lithium-ion battery as a substrate to make this flexible lithium-ion batteries. So because we can incorporate the active material into this porous structure, therefore we don't need to use a binder, we don't need to use a conducting additive, we also don't need to use a carbon collector because this foam is highly conductive. So then we can make a battery. This is a 4 battery, lithium-ion battery, which is flexible and has very good electrical conductivity during bent and flat state. And also very good cyclability, as I show you here. And because the active materials are very well incorporated into the graphene foam, with a close contact. Therefore, the rate capability is very good. As I show you the 10C, which means 6 minutes charge, so we can have very stable capacity. So that's very important because membrane, our flexible battery, normally is very thin. That means we cannot use many active materials. The total capacity is very, very low. So if we can charge this battery very quickly, so for example, when we drink a cup of coffee or tea, we can charge our mobile phone and then to be used for several hours. It is very good. So I think this high rate capability is very important for flexible battery. Okay. So I want to summary for my talk. We can use graphene and carbon nanotubes in different types of energy storage devices, from battery to supercapacitor to flexible devices. And also, those kind of material has different functions in energy storage devices, from active material to conductive network, and a buffer and protection layers, and also substrate our matrices. However, I think if we really want to use those nanocarbon material, we still have a long way to go. We need to have tonered material with very good controllability of quantity, and also we need to design composition, optimum composition structure and configuration for different types of energy storage devices. Because we are using nanocarbon, basically we have poor first Coulombic efficiency. However, if we want to have practical use in battery or supercapacitor, the first Coulombic efficiency is very important. So we need to improve this performance, and also the cyclic performance. Of course, another problem is the cost. So I'm sure some people will ask me how much for 1 kilogram of graphene material. So we need to lower the cost. And of course, from a scientific approach, we need to understand the mechanism. But I'm quite optimistic for nanocarbon to be used in electrochemical energy storage. I would like to thank my colleague, in particular Professor Li Feng. He is working with me on energy storage, and Liu Chang on carbon nanotubes, Wencai Ren on graphene material, and other colleagues. Those work has been accomplished by those PhD students. Some get PhD already, some are still working with us. And of course, we also have international collaborators and domestic collaborators. And the funding agency, everyone has those funding agency support. Finally, I want to make an advertisement. So 2 years ago, ISWIR invited me to be the editor-in-chief to initiate a new journal we call the Energy Storage Materials. So your high-quality papers are welcome to this journal. Probably we will have a quite high impact factor very soon. So Professor Kim at this university has contributed quite a few papers to this journal. Thank you very much for your kind attention.
Thank you very much, Professor Cheng, for your very comprehensive lecture on the use of carbon nanotubes and the graphene to boost the performance of batteries and supercapacitors. Thank you very much. Now, can I invite questions? Yes, please.
One is, as is known, such as the interaction between the metal oxide and carbon materials is very important because it can affect the maybe charge transfer resistance and the cycle stability. I wonder, are there any common ways to improve the interaction between those two components? This is the first question.
Yes.
And the second question is that, as you said, when introducing maybe nitrogen dopant into carbon materials, the nitrogen can contain different types, like pyridinic nitrogen or graphitic nitrogen.
Yes.
Yes. So I wonder whether there are some ways to control the type of nitrogen.
Yeah, very good question. The second one, as I mentioned, we have some calculation. Also, we try to have some nitrogen doping in single configuration, like as you said, graphitic, or pyridinic, or pyrrolic. And another one is amino nitrogen, right? So actually, when we have the nitrogen doping, we have different types. So we want to have a single type, but it's very difficult. Right now, we are not so successful. So the first question is about the interaction between metal oxide and carbon material. Yeah, as you said, it's very important. So we can improve the interaction between metal oxide and carbon material by functionalization. For example, we found that if we use graphene oxide or nightly reduced graphene oxide, which means we still have quite a rich oxygen-containing functional groups. By hydrothermal synthesis approach, then the metal oxide can form some chemical bond between, with the functional groups of graphene. So we call this in one of our SAS nano paper. We call this oxygen bridge effect. But that means the metal oxide, the metal through the oxygen of the functional groups to graphene, they can form quite a strong chemical bond. We have a proof from XPS and other methods. This kind of chemical bond really formed.
Yes.
Professor Cheng, I noticed that you have produced a lot of graphene membrane on nanotube membrane. Have you tried to fabricate the commercial lithium sulfur battery with this membrane because you introduced this membrane? And may I know the energy density and the anode of these batteries? Thank you.
Yes. So, and this again is a very important question because if we want to have a commercial lithium sulfur battery, anode is very important because quite many research work are focused on cathode. That means the sulfur part. But if we want to have a commercial lithium sulfur battery, every part is important, including anode. But if we use lithium as anode, we have many problems. That's why we don't use lithium in lithium-ion battery, because it causes a safety problem. In lithium sulfur battery, it's similar. So we cannot make commercial lithium sulfur battery right now because we don't have suitable anode material. So that's why in particular in recent 2 or 3 years, many research groups, including Yi-Cui's group, I heard he gave a talk here in January because he told me, quite a few groups are focusing on anode part. So if we can improve anode part, probably with this kind of membrane, we can make some practical commercial lithium sulfur battery. But we do make a full battery, lithium sulfur full battery, using lithium metal. But the cyclability, as you may know, is not so good. Maybe 10 or 15 times we cannot use.
Okay, yes.
Thank you for your excellent talk. I have a question about the issue of these your nanocarbon-based device. If you increase capacity or cyclic performance, what happened to the mechanical strength of this material during operation?
Not many people are working in this part. I just read quite a few papers on this mechanical deformation during charging and discharge, but it's very important. In particular for the very big battery. That's why Tesla only uses the small battery. If we have a big battery, the safety is a problem. Another problem is, as you mentioned, the mechanical deformation. But really, we haven't worked in this aspect, but rare people working on that. Maybe that's a good research direction, I think.
The second thing is you come with all kind of nano material, right? So once you make the real product, I don't know what's the potential impact in the environment. Because people know some nano material is toxic, some biological species or humans. So that what is any comment about the environmental impact?
Carbon nanotubes have quite many people have investigated the environmental impact on human beings of carbon nanotubes. But the results is complicated and in some way contradictory. Some said it's harmless, but some said it's like asbestos, harmful. 石棉是 asbestos.
Fiber.
Asbestos. It's harmful to human beings. But for graphene, the research is not so many, but the results is more positive than carbon nanotubes. But again, we use many nanocarbon actually. Like tire, we use carbon black. Carbon black is a kind of nanocarbon particles. So that means in our atmosphere, there are many nanocarbon particles. So maybe graphene should be similar to that kind of material, but the carbon nanotubes is a very small one-dimensional material. Maybe it's more harmful, I think.
Yeah, my question is actually on the least fancy application. It's probably easier for me to understand. So in one case, you use a graphene coating on a current collector to improve the rate capability of a lithium iron phosphate electrode.
Yes.
And that coating was put onto a metal current collector.
Yes.
And normally when you think you put additional layer onto a metal piece of metal, you increase the resistance and actually decrease the rate capability. Except that in one case, your contact resistance is actually dominating your battery's performance. So may I have your opinion on why this is actually happening to your battery?
Yes, it's very good. So theoretically, you're right. If we put something directly on metal surface, the electric conductivity should be better, right? But considering the energy material, the active energy material is particles, and they are very poor adhesion between metal current collector and the active materials. And also its particles, that means the contacting area is not 100%. So if we put a very thin graphene layer, or some people also using carbon nanotube layers, so we can control the adhesion between the metal current collector and the graphene suspension. And also, after this coating, basically this layer is not smooth. They have a very rough surface. And it's a kind of porous structure. So we found that they have a very good adhesion between this coated layer, a coated current collector, and material. Adhesion is improved. That means the electrical conductivity is improved. Second, it's not so easy to detach during charge and discharge between the current collector and the active material. So that also can improve the cyclability.
Professor Cheng, thanks for your kind talk. My question is, as lithium-sulfur battery has been developed for so many years, in your opinion, what will be the most promising cathode architecture for higher sulfur loading and improved cyclability? Will it be a freestanding electrode using sulfur as active material, or solid-state sulfur-impregnated electrode?
I didn't catch you clearly. You mean, lithium-ion battery is developed for many years. So the second part, what do you mean? Polysulfide?
I mean, what will be the most promising cathode architecture for lithium-sulfur?
Architecture, not material
promising architecture for lithium-sulfur batteries. I don't know. I don't know most of the promising one. So there are many types. So for example, we can use active carbon, methyl-porous carbon to host the active sulfur and polysulfide. But I think we need to find someone to have a very high sulfur loading and sulfur content. This is a common problem for other materials, for most of carbon materials, because the sulfur loading and the sulfur content is quite low. So if we really want to use lithium-sulfur battery, the cathode part, we need to increase the loading and content. So I don't know which one is the optimum or most promising configuration, but I think the configuration needed to consider this two parts.
All right. Before we go to a coffee break, on behalf of IAS, let me present a small souvenir.
Okay.
Thank you very much.
Thank you.